Hi everyone, my name is Amitesh and this is a special lecture series on real analysis starting off with the theory of sequences. So here we're going to rigorously prove fundamental facts about sequences that we take for granted in calculus, for example. So here we have limit n goes to infinity of an is a, limit n goes to infinity of bn is b. We want to show that the limit of the sum of the sequences an plus bn is the sum of the limits a plus b. So I'm going to talk briefly about sequences and limits and convergence, so don't worry, I've got a previous lecture where I introduced these, to check that out as well. But basically the point is that a sequence is a tuple of numbers, so a1, a2, dot, dot, dot. We have another sequence which is a tuple of numbers, b1, b2, dot, dot, dot. So b1, b2 denotes the first, second, etc. terms of the sequence. And then we define the sum of the two sequences to just be adding the terms point-wise. Okay, so a1 plus b1, term by term, a2 plus b2, dot, dot, dot. Okay, and we want to show that the sum of the two sequences in some sense converges to the sum of the limits. It seems intuitively obvious, but we want to go through the epsilon definition of convergence. Okay, so the epsilon definition of convergence says that if you take the limit of, for example, the first sequence, which is a, let's say you're on the number line, you have a, no matter how much I zoom into a, how specific I get, okay, so I take a really small open interval containing a. So this could be like a minus 1 over 10 to the 6, like a million. And then be a plus 1 over 10 to the 6. Okay, no matter how close I get to a, eventually the terms in the sequence will be in that interval. So eventually, so there exists an n, so there exists a big N such that the absolute value of an minus a is going to be less than whatever the degree of specificity is. Okay, so here we said 1 over 10 to the 6, we generally call it an epsilon. So there exists n so that this is less than epsilon for each epsilon at least 0. Okay, so saying that absolute value of an minus a is less than epsilon, I've done lots of videos on my channel on absolute value, very basics, but that's just the distance from an to a. So that means that an is in this interval. So we want to show that the limit of an plus bn is a plus b, we want to show for each epsilon there is a sufficiently large index so that all the terms in the sequence an plus bn are within epsilon of a plus b. We know that that's true for the sequences an and bn. Now we have to show it's true for the sum. So here's the proof. Here's the way we construct it very rigorously. You know, I'm just going to teach you this in a very simple way. So the first thing is we want to show, so let's kind of just write out the proof. So I'm going to put it on this side of the board. We want to show for any degree of specificity that we can get within that degree of specificity of a plus b. So the proof is going to be as follows. So proof is we're going to say that let epsilon greater than 0. Okay, that's how all convergence proof starts. Whenever you have any sequence convergence proofs, let epsilon greater than 0. Now we want to know, we know that like an gets close to a and bn gets close to b, right? We know that. We want to show that an plus bn gets close to a plus b. So before we kind of go on with the proof, let's think about what does it mean for an plus bn to be close to a plus b to guess how we proceed. Okay, so an plus bn being close to b, well, we're looking at the distance, right? An plus bn minus a plus b, right? So for an plus bn to be close to a plus b, we're looking at that difference. Now that difference is going to be the same as, how do we sort of think about it? We know that an gets close to a and bn gets close to b. So let's compartmentalize that. Let's say that an gets close to a, so we can sort of look at an minus a. That's going to be something we'll understand. And this is the thought process. And then we look at bn minus b. So I've kind of split it up into two pieces. Now we know that this piece is small and this piece becomes small. Okay, as n gets large, we know each of these pieces gets small. We want to show the sum also gets small. The absolute value of the sum gets small. And the absolute value is because we don't care about the sign, just that it's small. Okay. Now, when we look at that, the key thing we want to think about is the triangle inequality, because we want a relationship between this absolute value and the absolute value of an minus a, which we know becomes small by the first limit, and the absolute value of bn minus b, which we know becomes small by the second limit. The triangle inequality is the perfect ingredient, the secret sauce, for basically saying that it says that, and I have a video on my channel on the triangle inequality. Check it out, I proved it there. Okay, so if you want to prove it and deeply understand it, check out that video. I've explained it like as a sort of principle that the journey is what matters, not the destination, which is a life principle. But I've explained it that way in that video. But here we have absolute value an minus a plus absolute value bn minus b, and we know that we can make each of these terms small, so therefore we can make this small. Now here's the next step. Before we proceed with the proof, what does small mean? We want it to be less than epsilon. So we want these two terms to add up to something less than epsilon. So what do we have to do to make it less than epsilon? Well, if each term is less than epsilon, the sum will be less than 2 epsilon, which isn't exactly right. Now the formality of epsilon proofs is we want it to be less than epsilon. Okay, we fix the epsilon and then you have to say it's less than that epsilon, not less than something else. Okay, even though actually it's not going to matter in this case, it's still important to get used to that thinking with rigorous math. So what we want is we want to make sure that each of these terms is less than epsilon by 2. Once we do that, the sum is going to be less than epsilon. That makes sense. You're adding two things, you want it to be less than epsilon, make sure each is less than half of epsilon. So now what we do is we say that epsilon greater than 0, since limit an is going to equal to a, there exists n1, okay, there exists n1, and here's another important point. Why do I say n1? Because the rate at which an gets close to a and bn gets close to b is not uniform. You know, an may start getting very close to a after the 20th term, but bn might start getting close to b after the trillionth term. It doesn't matter as long as eventually it gets close. It doesn't matter what it does at the beginning. Convergence doesn't care about that. Convergence only cares about the limit. So we need to keep that in mind. We need to make sure that we take care of both the rates of convergence separately or uniformly. So here we say there exists n1 such that the absolute value of an minus a is less than epsilon by 2 for n at least n1. Okay, so I'll say for the index, for little n at least n1, that's going to be true. Okay, so we're going to have that an is within epsilon by 2 of a, which is what we want. And then we know similarly, since the limit as n goes to infinity of bn is equal to b, there exists n2. So this is a very rigorous way of constructing the proof. There exists n2 such that, and I'm sort of going to put an arrow here, such that the absolute value of bn minus b is less than epsilon by 2 for n at least n2. Okay? Now here it doesn't matter whether you say at least or greater than. Some people say greater than, some people say at least in definitions. It's the same thing because you can just add 1 to it. You know, if this is true for n at least n1, that's the same as saying it's true for n greater than n1 minus 1. Okay, so it doesn't matter whether you have an inequality or an inequality or a strict inequality there. So here you're going to have this. Now you know that therefore this. So I'm now actually going to just do something tricky. Not tricky, but like sort of like cheating. I'm going to, what we've just written, I'm just going to append it to the proof. Okay, so I'm going to say that like, therefore for n greater than or equal to the maximum of n1, n2. Okay, so n greater than the maximum of n1, n2. What is that? That is the bigger of the numbers. Okay, so once n is beyond n1 and n2, we know that an plus bn minus a plus b, the absolute value is going to be less than or equal to epsilon by 2 plus epsilon by 2, which is less than epsilon, and that is used the triangle inequality. Okay, so that's going to be the end of the proof.